Okay, this question again has a bunch of random vector identities, and I'll go ahead and share the videos or links with the ones we use since they go back all the way to chapter 1 and we use certain parts of them. But nonetheless, let's dive into the question. So we have to consider an ideal stationary magnetic dipole M and a static electric field E. Show that the fields carry a momentum P equal negative epsilon naught mu naught M cross E. All right, so, well, let's go ahead and dive into what we know the definitions are. So if we start with the momentum stored in the fields, we get P is equal to mu naught epsilon naught, the volume integral of S d tau. Okay, but if we plug in what S is, and we get 1 over mu naught E cross B, and you see the mu naughts cancel, easy enough. But since we have a curl here of E cross B, we need to put things in terms of other things that we know. Since the electric field was static, we can go ahead and plug in the assumption of the gradient is equal to the field, negative gradient is equal to the electric field. Since the electric field being static allows us to do so via Laplace's equation, all that other stuff that we did in chapter 2 and 3. So we substitute that in, pretty easy money there. And then we go ahead and push the minus sign out, and now you see that we have in the purple a gradient V cross B, okay? So as you might imagine, what we're going to try to do is put this up to where we can have a identity where we can substitute in and use things like the divergence theorem or things that we know, okay? So theorems that we know. So let's go ahead and pull up the product identity or the product rule of the curl of some scalar function f times a is equal to f times the curl of a minus a times the gradient of f. Okay, here a is just some random vector, not necessarily the vector potential for magnetic field, and f is some scalar function. So for our setup, f is equal to v and f is equal to v and a is equal to b. All right, so plug it in for our context, and we see that applying this product rule, we get v times the curl of b minus b times, or cross product, the gradient of v. So if we solve for this, what we see here is that we have b cross the gradient of v is equal to v curl of b minus the gradient, the curl of v times b. Okay, so we don't really have that in a purple yet. We need to change the order, so we apply a minus sign in order to change the order of the cross product. So if we apply a minus sign to the left-hand side, we have to apply it to the right-hand side. Okay, so what we see here to cancel that, we apply it to both sides, we factor the negative sign out on the right-hand side to cancel with the left-hand side, and now we're ready to substitute in. All right, so now we can sub this in and break this integral down. So we still have P is equal to negative epsilon naught, volume integral of the curl of V times B, and then minus V times the curl of B. Okay, d tau. So if we separate this into two integrals, what we see here is that we have negative epsilon naught, volume integral, curl of VB, and we have positive epsilon since we distributed the negative, V curl of B, d tau. So we see that the right-hand integral is Ampere's law, nice to deal with, and we see that the left-hand integral is actually equal to a problem that we solved for back in chapter 1. Again, I'll go ahead and link them so you're not stranded. And what we see here is that this is equal to negative, since we have a curl, we can apply Stokes' theorem, VB cross dA for some integral for some surface S, and that cancels to 0, which I'll explain soon. And then we have plus epsilon V integral V times, now substitute in Ampere's law, so we get mu naught J plus mu naught epsilon naught times the partial derivative of E with respect to T. But again, we were told we were a static field, so that E term goes to 0. That was the easiest part of that. Now V is over all of space, and S is a surface at infinity, where physically B goes to 0. Okay, it's part of the boundary conditions with these solutions. So what we want to know is that for a current confined to an infinitesimal neighborhood of the origin, we can approximate this potential. right? So if we have V of R, we can approximate this to V at this origin plus the rate of change of V dot R. Okay, so the gradient of V dot R, which we know here is equal to V naught, and the gradient of V is equal to negative E, but again, it has to be at the origin times R. Okay, this is again an approximate, so let's run it through. So all that we're left with in this momentum integral is epsilon naught mu naught, again from Ampere's law, and then, and so we have V times the current density d tau. Okay, so if we plug in the approximation for V within some infinitesimal neighborhood of the origin where everything can hold tight, okay, then we can distribute the current density in and we can model everything there. Okay, so here we pull out V naught, or excuse me, V at the origin for one integral and epsilon naught, and then we have E naught, or E at the origin dot R, and then both of them multiplied by J d tau. Okay, but here for a current loop, since we know that the volume integral of J is equal to the line integral of I, okay, due to dimensional sake, we could say that I is equal to the volume I times the line integral. Well, that's equal to 0. It's a closed loop. It circles in on itself. All right, so with that being the case, the volume integral for the V of 0 point goes to 0, and we're left with, here in this case, we have E of 0 dot R times I dl, okay? So we can't necessarily break that through all the way, since that's not a full integral. We have a product there. And then, of course, this E dot R dl that we showcased here, we factor out the I. Well, that was another problem back in Chapter 1, which again I'll link. And then we see that that's equal to A cross E at 0. Okay, but if we factor in I, since that's the area, if we factor in the I back into A, what we see is that we have I times the vector area, which is M. Sure enough, P is equal to negative epsilon naught mu naught M cross E. What a wonderful result. And guess what? We'll definitely use it. That's why he has us doing it.